Any difficult problem arrives as a dense, shifting mass of facts, emotions, and contradictions. To see what it's made of, you first have to stop looking at the whole thing. When you face a day that arrives in pieces, the mind naturally panics. If you try to process all that noise at once, the system simply freezes. Clarity starts with decomposition. This is the act of ignoring the chaotic pile to isolate the smallest working part. We pull the knot apart into 3 specific chunks: identify what happened, find the repeating pattern, and observe the consequence. This sequence of isolating parts functions as the common starting point for a student learning and an engineer building a model. High-volume data is just noise until it's sorted into a hierarchy. Understanding begins where the pile ends and the structure starts. Let's look at how that structure forms. Imagine noticing that evening tea sales at a cafe rise every time there is early afternoon rain. The human brain is an energy-saving machine, so it's quick to assume the rain causes the sales. We often miss hidden variables, like a drop in temperature or a shift in foot traffic, because jumping to a conclusion is faster. Algorithms approach this by measuring the exact distance and similarity between data points. They don't make assumptions. They simply calculate what naturally groups together. This scatter plot shows how an algorithm processes information. It maps abstract data points, grouping nearby dots into clusters based on mathematical proximity. The result is a representation, a structural map preserving statistical relationships while leaving physical context behind. Because these representations are only maps, they are limited. They can only reflect what was recorded, and they remain blind to whatever reality was left outside the doorway of the data. A map alone is static. To turn that structure into a system that actually learns, we have to introduce a continuous cycle. This closed-loop flowchart illustrates the cycle. Information enters, the system predicts, acts, measures loss, and returns data. Without feedback, it isn't learning. Backpropagation adjusts future attempts based on loss, just as the gap between intention and result changes human behavior. Learning in any environment requires friction. We have to use the measurement of our mistakes to adjust our internal weights before we try again. A perfectly learned rule can still lead to a flawed outcome. If a person decides that emotional connection is a danger because it can cause pain, they are optimizing for safety, but they are losing life in the process. Machines optimize rules flawlessly, but they possess no awareness of whether those rules are wise. They maximize a metric without understanding the purpose behind it. These systems search for the most probable path through their training data. In that search for the statistical middle, the unusual detail, the unique human exception, is often discarded as noise. Optimization provides speed, but without context, it becomes a race toward a result that no one actually intended. Complexity is manageable when it's divided. We can take that initial knot of noise and replace it with a readable mental structure. This diagram maps the process for navigating an uncertain world. We understand the goal, simplify the parts, question the patterns, and test the model before we commit to a decision. This is what it means to be the human in the loop. It is the choice to remain responsible for the purpose and the boundaries of the system, rather than just pressing approve. One specific decision to adjust a threshold or verify a source acts as an initial input. That single beat initiates a sequence of effects that widens as it travels through a life or an organization. Speed can light the road, but speed is not wisdom. The tool provided the shape, but only the human provides the honesty required to decide the final turn.